Welcome back, I'm that chemist, and today we have 5 important papers in organic synthesis for the month of May 2023. The first paper for today is the total synthesis of daphthinolonin B. Some highlights of this paper include the first total synthesis of daphthinolonin B, and the authors used several different creative reactions that I was quite pleased to see. If you're the type of person who enjoys seeing obscure reactions used in creative ways, this is the paper for you. I'm going to be showing a few highlights from the paper, but I'd encourage you to check out the whole paper where they have even more examples. A number of the members of the class that daphthinolonin B is from have interesting bioactivity that may be of interest to medicinal chemists in the future. But to me, I'm a synthetic chemist, so we're going to talk about some of the cool synthetic chemistry that they did in this total synthesis. I want to highlight a couple examples, such as the conversion of 10 to 12. 10 is orthocresol, and they were able to do an oxidative dearomatization and add in this diol to the para position relative to the phenol, giving this masked benzoquinone product. I particularly like seeing oxidative dearomatization reactions, and this is just an iodine-3 reagent that's able to oxidatively dearomatize the corresponding phenol. In addition to this transformation, the authors also had this interesting 5+2 cycloaddition. If you're an undergrad or a new researcher, this would be a good one for you to practice and actually write out. Sometimes in the That Chemist Discord, we have problems of the week, which are not weekly, but we have them whenever we have them, and this is the current problem. If you'd like to go take a stab at there's a whole community of organic chemists that would be interested to discuss more chemistry with you. In addition to this transformation, where using Bock anhydride, they were able to convert this hemiacetal into this corresponding tricyclic system, the authors were subsequently able to do a radical cyclization reaction of this trichloroacetamide, adding into this vinyl acetate and deprotecting to afford the corresponding ketone. In a second step in the same pot, they then undergo reductive dechlorination to afford the corresponding product 18. As I said earlier, there's a lot of cool steps in this chemistry that I'm not going to discuss here, but you should go check out in the whole paper. But one thing that I saw that I haven't noticed in a total synthesis before is the use of a Chug elimination. So I'm only familiar with Chug elimination because I've done way too much thiocarbonyl chemistry in my time, and this is an example where the Chug rearrangement was actually useful. So what the authors did is they deprotonated this alcohol with sodium hydride, and then upon treatment with carbon disulfide and subsequently iodomethane, they were able to make the methyl xanthate. They additionally did a second step to install a methyl group at carbon 18, and then they underwent a thermal Chug rearrangement that also facilitated a Wagner-Meerwein rearrangement. So instead of your typical Chug elimination where you'd immediately get a double bond, they also have a rearrangement of their skeleton, affording product 23. They then undergo a second Chug rearrangement, except in this case, the expected double bond is formed. I also want to highlight that this is not only an alpha, beta, gamma, delta unsaturated, as we see in 23. In 24, we have an alpha, beta, gamma, delta, epsilon, zeta carbonyl. So this is a very conjugated system, but it's important to remember that there's quite a bit of 3D structure to this molecule. So that's why this is stable in all likelihood. Now, the conditions for a Chug rearrangement are rather harsh. That's why orthodichlorobenzene is used as the solvent, and you can see that this is done at 180 degrees, so the fact that this whole molecule just tolerates that is quite impressive. Now, a couple other steps just to finish off here. We have the samarium iodide-mediated ring opening of the epoxide, but what I really want to highlight is this saponification of the corresponding ester, followed by an MCPBA-mediated decarboxylation, presumably occurring through the per ester, as they're using DCC as a coupling reagent, allowing them to isolate compound 27, which is kind of funny to me. I don't know why it's funny, but it's kind of weird to see a M-chlorobenzoate in a natural product synthesis paper. Okay, so afterwards they do some functional group interconversions that affords the ketone, which is their final compound, daphthinolonin B. The next paper for today is Photocatalytic Denitrogenation. In this case, we have a bimolecular reaction affording a new CC bond in the product, and this was done using amines and O-nosyl hydroxylamines as coupling partners. This is a photocatalytic diazine-mediated process, which is quite similar to work that we've seen from the Levin group in the past. The mechanism of this reaction is as follows. First, we have diazine formation in the presence of air as the oxidant, as well as through the elimination of the nosyl group. Once the diazine's been formed, it's possible to undergo a photocatalytic denitrogenation using their iridium photocatalyst, and the two subsequent radicals are able to terminate, forming the coupled product. The scope of this chemistry was quite good, tolerating a wide range of functional groups, although for the most part they tended to use this highly substituted O-nosyl hydroxylamine. A number of functional groups were well tolerated, and they even did this on derivatives of amino acids to show that this was an amenable process. It is worth noting, however, that when we have a group in the 3 position, this led to poor diastereoselectivity, and I would assume that this is because the radical at position C is able to racemize before it's able to couple with the radical in position A. They also showed that when lysine was used as a substrate, it had preferred reactivity at the terminal nitrogen of lysine rather than the amino group alpha to the carboxylic acid. They also showed that this would work on natamycin, a natural product, affording this isopropylated product in the presence of a large range of functional groups. Trying to make stuff like this would be really challenging unless you had the knowledge that this group had. It sure would be great if we had a tool that helped us make complex molecules like this. Oh wait, we do. Are you a scientist searching for new ways to synthesize molecules? Look no further than this video's sponsor, Reaxis. Imagine this. You've successfully created a molecule, and now you're curious if there are alternative methods to create it. That's where Reaxis comes in. By simply navigating to Reaxis and searching for your molecule structure, you'll discover a plethora of possibilities for a new synthesis plan. If we click on the red flag for published results, we can find preparations for structures that are similar to the compound that we built. And by utilizing their powerful synthesis plan tool, you can generate retrosynthesis plans. These plans serve as a catalyst for your own ideas, and though you may need to tweak them to suit your needs, Reaxis is a source of inspiration. But wait, there's more! Reaxis allows you to customize your search by selecting specific parameters. Choose from building blocks supplied by top-tier vendors, decide how many different routes you want to explore, and even play with the diversity of proposed predictions. Talk about tailored synthesis. Once you've set your parameters and initiated the search, Reaxis processes the data. Soon enough, you'll have a selection of predicted routes at your disposal. Clicking on the View button reveals a collection of suggestions. It may surprise you that some of these bear a striking resemblance to routes mentioned in published papers. Reaxis draws inspiration from known compounds and leverages previous reports to propose novel synthesis pathways. Reaxis gives each of the examples a score of how similar it is to the published reaction in the literature. Keep in mind that you can further refine your search by adjusting the processing time. Whether you need fast results or prefer to give Reaxis additional time for its predictions, the choice is yours. While the routes presented may not be the ultimate choice for your final API, they serve as invaluable stepping stones towards discovery. These suggestions are incredibly useful, providing fresh perspectives and creative synthetic ideas to enhance your research endeavors. I'd like to thank Reaxis for their support of this channel. The third paper for today is radical hydrocarboxylation. In this work, the authors reported hydrocarboxylation of terminal olefins in a photochemical thiol-mediated process. The authors ended up finding out that they didn't actually need a photocatalyst like 4-CZ-IPN or related ones to mediate this process, and a lot of the paper is dedicated to a discussion of this. I'm going to gloss over that part because I'm a synthetic chemist. I care about synthetic utility. The mechanism of this paper is relatively straightforward. They have their thiol under photochemical conditions. This can form their disulfide, and their disulfide can form sulfur-centered radicals. Sulfur-centered radicals are necessary to facilitate this process, taking formate to its formal radical. The formal radical can then couple with their terminal alkene at the terminal position, making an alpha radical, which is able to abstract a hydrogen atom from the thiol in their system, regenerating their sulfur radical, which then continues the cycle. Their final carboxylate will be protonated in workup to afford the corresponding acid. As I mentioned before, terminal olefins tended to be the scope of this chemistry, but I'm not showing every single example from their scope here, so if you'd like to see more examples, I'd encourage you to check out the full paper. A number of complex functional groups were well tolerated, and the authors even scaled this up to a 10-gram scale. This was done in batch rather than flow, and instead of the cesium formate that they'd used earlier, they demonstrated that potassium formate could instead be used as the formal source. This process didn't require any chromatography, and no precautions to exclude air were required, and the product could be easily purified with aqueous extraction without the need for chromatography. The fourth paper for today is from Patrick Fear at Merck. If you haven't read Patrick Fear's papers before, he's authored some real bangers. And this one is no exception. This is a really useful paper. Some highlights of this paper include a simple conversion of esters to ketones, especially acetophenones, as methyl ketones tend to be the most common type of ketone that people want to make to do chemistry with. In this paper, alkyl sulfonates were used as nucleophilic methyl and alkyl donors, and this works because they were able to stabilize the carbanion intermediates to prevent overaddition of their ketone or of their nucleophile. The mechanism of this paper has two potential routes that they end up examining later, and we'll get to what the actual mechanism was later. You could imagine two possible mechanisms where the sulfonate's been deprotonated by a second base. I haven't showed it yet, but they also use lithium HMDS to deprotonate the alpha position of the sulfonate, which can then act as a nucleophile and displace the alkoxy group of the ester. Once the sulfonate's been formed, aqueous workup would be sufficient to afford the ketone through the elimination of sulfur dioxide. However, it's also possible that a glycine type intermediate would be possible, where an enolate is formed, and through subsequent elimination of sulfur dioxide, we're afforded with the final ketone. So make sure you stay tuned to the end of this, where I'll get into that a little bit more. The scope of this chemistry was quite good. Functional groups such as aryl iodides, nitriles, and heterocycles were all well tolerated. They also demonstrated this on a BCP-containing derivative, which is cool to see. You know I like BCPs. and even this indole was tolerated. There were some limitations, as alpha protons were not well tolerated. This tended to form the enolate of the corresponding ester, and they didn't want to do that. If they had an aldehyde, that's another competing electrophile. This could react with their nucleophile, and they saw loss of the tosyl group in this case, and these two sulfonates didn't work very well for different reasons. I mentioned earlier about the mechanistic investigation. So by doing trapping experiments with different deuterated proton donors, they were able to compare the ratio of mono, di, and tri-deuterated products. Here you can see that the di-deuterated product was the major product that forms, which suggests that it's a mechanism analogous to Claisen condensation. So I personally really enjoyed this paper, and I look forward to seeing this chemistry get used more and more, as methane sulfonate is a very accessible methyl source, and I would say it's definitely preferable over something like methyl magnesium. The fifth and final paper for today involves skeletal editing, where BCPs were made from the corresponding aza BCHs using Mark Levin's reagent as a means of deleting the nitrogen. The way that the authors did this was by first forming an imine, which could then be converted to the trifluoroacetamide enamine upon treatment with trifluoroacetic anhydride. Once this enamine is formed, it can then undergo an intramolecular 2+2 cycloaddition, followed by subsequent nitrogen deletion to afford a BCP scaffold. Here you can see what the diazine would look like before it was eliminated, and before the radicals could recombine to afford the final BCP. The scope of this chemistry was quite good. The authors tended to focus on substituting what this green group was with a number of different heterocycles. In this case, you can see this NH-Bach group is present on all of the examples in this scheme, although the authors do have other schemes in this paper that I would encourage you to check out. This chemistry works quite well. This is the structure of Levin's reagent. If you haven't seen it before, we've talked about it a couple times on the channel previously, and this is one of the contemporary reagents used for nitrogen deletion strategies. In addition, the authors demonstrated a gram scale sequence starting with 5 grams of this precursor, which were ultimately converted into 22 as well as Epi22. I think that this chemistry is quite cool. It's nice to see another way to make BCPs, especially where we have diversity on the side of the BCP rather than the other terminus, and I'm excited to see this chemistry get used by more groups in the future. We also have a handful of honorable mentions for this month, and these are all worth reading if you haven't checked them out yet. I'm expecting that in June, there may not be an important papers video published, as I have quite a busy month. I'm planning to defend my thesis in the early fall, so I'm going to be a bit busier than usual, but there will still be some uploads on the channel in the coming months. Thanks for your attention, thanks for watching, and I hope you have a great day. Nitrogen of lysine, rather than